There we go. Okay, and that just about wraps up lecture for today, everyone. Sorry for going a little bit over time. If you have questions, I'll stay here for a little bit to answer them, or you can come visit me in my office hours. Thanks. Wow, what a great lecture. Let me go ask him a question. Professor, where'd he go?
What the? Why is this man so short? From the back of the class, he seemed to be a normal height.
Yes, did you have a question? Yeah, I had a question. So I was wondering, why is it that like photons, or the photons that can eject electrons, in the photoelectric effect are always like the shortest? Haha, yes, you mean in terms of wavelength. Well, that has to do with the equation I wrote on the board earlier. E equals hc over lambda. The shorter the wavelength, the more energy a photon has. So in some ways, it really is the tiniest, most itty-bitty things that have the biggest impact. Yes, I suppose so. Ah, that's why you have a Nobel Prize. I'm sorry? All right, I feel like this would be a good place to pause for questions. Yes.
Yeah, so I was wondering, when we're doing calculations with like extended Huckel theory, all the matrices, or I guess H, are symmetric. Why is that?
Ah, that's right. Thank you for the question. Well, the Huckel model is actually an oversimplified model that works well specifically for pi conjugated systems. But it turns out that actually any Hamiltonian matrix consisting entirely of real components must be symmetric. That's because Hamiltonian matrices are quantum operators, and quantum operators are always Hermitian matrices. That's what the theory of quantum mechanics tells us. Hermitian matrices are matrices that are equal to their complex conjugate transpose. And so for the case of a real Hermitian matrix, because all of its components are real, its complex conjugate is just itself, which means it must be equal to its transpose, which means it must be symmetric. In fact, back when I was a graduate student down in Australia, I remember reading Charles Hermite's first ever paper on Hermitian matrices, and it led me to take a deep dive down into the depths of quantum mechanics, and as I read Werner Heisenberg's first ever formulation of theory
quantum chemistry.
Entirely
Back in Melbourne, I even had a crab,
Hermitian
hermit
matrices.
Hermite such a matrix,
who I named
it actually ends up giving you really beautiful results
that's
in
why
its
I have a job.
eigenvalues.
That's why that's how I sadly ended up contributing to the creation of the world's first hydrogen bomb. That should do it. Okay, I think that's all I have for lecture today. Can I take any questions? Yes. Yeah, you. Yeah, you. Yes. Yes, please ask your question.
Could you explain which potential is oxidative and which is reductive on a CV?
Absolutely. Let me explain that again. Let me get some more board space. All right, so well, that's quite interesting, isn't it? I wonder who drew that. Maybe they thought they were funny, but they were more phallical, in a sense. Sorry. Okay. All right. Back to your question. So we were talking about CVs, right? You were asking about CVs. Maybe I should start with an example. Let's do that. So let's take an example of some work that one of my graduate students has been working on, which is looking at hydrogen evolution with platinum electrodes. And one thing we do is take CVs of these platinum electrodes, and I'll draw out what these CVs look like, and then I'll sort of explain what they mean. So let's get to it. Drawing a CV. So we have voltage, and we've got current. Okay, so let's ignore the exact voltage scale. This line here might not necessarily be 0. When you're dealing with a CV like this, you often start sweeping left to right, in other words, from negative to positive potentials. And with platinum, that will sometimes look like this. Like, boom. All right. So that's our positive sweep, and we get a positive current. Now, let's sweep back this way, and we end up going from positive to negative potentials, and we'll end up with a negative current. So, all right, and so this is often what our CV looks like. And so the important part about these kinds of CVs is this part. Now, I smooth this out. Usually it'll look something like this. This is called hydrogen under potential deposition. But we won't get into the kinks of that, which is why I smooth it out here. But these two big guys are actually really, really important. And that's why I've circled them here. Oh God, what have I done? Well, I didn't mean to redraw phallus here, but it looks like it just happened. So let me. Okay. Damn it, Sheldon. Did that answer your question?
This is the worst.